Hi there, math fans. I'm Dr. Andy Lovelace, longtime instructor at the University of Washington. As I've been thinking about baseball season and batting averages, I've been playing around with fractions, and I happened upon this thing. But before I show you this idea, which I think is amazing if you've never seen this before, I'm just going to show you some visuals. So I was exploring what batting averages can happen, after 10 at bats, after 20 at bats, and I started to just consider all the fractions. And this is the visual I made. You're going to see at the bottom of your screen. So I started just to list the fractions, and I made it go up if it occurred more than once. So just think about this for a second before I tell you all this stuff. And I was very pleased with this visual. You can see there's kind of these little gaps, which is part of what I'm going to talk about in a future video about batting averages. But I found that pretty stunning as a visual that we could see this thing. And ultimately we saw there's kind of these holes. Okay. I realized as I made that picture, I was like, well, that is amazing. I thought it was awesome. It reminded me of these things called Farey sequences, which really are vital in number theory, which is actually my... We're surprisingly getting to something that I actually did research on once. But this is pretty amazing. And so I just wanted to show that I was really pleased with this visual I made. And I'm going to have more visuals here in a second. But I just thought it was pretty neat to see this. So I'm going to show you that one more time. These are all the fractions. Like if you only have had like 2 at-bats, these are all the halves, the thirds, the fourths, the fifths. And in a future video, like I said, I will talk about the fact that it's hard to bat around. You can bat 333, but it's hard to bat a little above and below. And it has to do with small denominators. These are all the fractions you can get with small denominators. And it leads to these interesting patterns and these repeats. We know there's repeats when you talk about 2/4 or 3/6. Okay. There's a whole theory to this. It involves this operation of adding fractions incorrectly, and it actually means something. I'm afraid to make a video like this because now students will start adding fractions incorrectly. But if you've never seen this, it is, like I said, pretty spectacular. And so I wanted to show you. Okay. As I was studying it and sort of rediscovering things, I was like, oh yeah, I do know something about this. So anyways, I'm going to show you a few things. So this is called the Farey sequence. I actually looked up the history, but I think I will save the history for a second video because my videos are always too long. That's what everyone tells me. I can't help you. I like to be complete. So I'll just show you the basic idea, and then I'll follow up with some history. So here you go. Wikipedia has this wonderful visual. It says we can use it. So here's what's happening. I'm gonna show you, and maybe before we do that, let's play the game a little bit. So the game is this. So we're going to write down 0/1, and we're going to write down 1/1. And then I want you to think about the next denominator you can have. Well, it's 1/2. I'm going to put it in the middle here. Now I want you to think about the next denominator you can have. Well, it's 3. And we're going to avoid putting repeats up here. But I'm going to put right over here. I'm going to put it directly in between, even though it's not directly in between. So I'm going to write 1/3 right here. And I'm going to write 2/3 right here. And what this actually is, a British geologist recognized this, which is that there's an interesting connection between adjacent numbers here. And the connection is to add fractions incorrectly. If you add the numerators and add the denominators, you get the fraction between them with the next biggest denominator. That's generally true. And it works over here too. It is amazing if you've never seen that before. It's actually practical when you're trying to approximate fractions. Like you're like, oh, it's not close enough. I'd like the next one closer. You add adjacent fractions. Most people have never seen that because it's dangerous to tell anyone this. But let's do it again. So we're going to do 0 plus 1, which is 1. And we're going to do 1 plus 3, which is 4. Notice how that's the next biggest fraction. Now 2/4 is right in the middle. But that's not how we do this. We next are going to add, we're going to do 1 plus 1 is 2. And then we're going to 3 plus 2 is 5. And so that's the fraction with the denominator 5. And then we have 1 plus 1 is 3. 2 plus 3 is 5. Incorrect. This is called Farey addition, named after this British British geologist. 2 plus 1 is 3. He didn't actually study it. He recognized it, published a paper, and then this mathematician, Cauchy, studied it in more depth, and more people studied it later. This is all the fractions you can get without repeats up to denominator 5. And that's the so-called Farey sequence. And you can keep going, but I'm going to stop there. And here is from Wikipedia the sorted Farey sequence up to denominator 8. Lots of interesting questions we can ask. How many are there in a given row? Where are the gaps? There are big gaps in various spots, and this is what got me thinking about this again, because in order to study batting averages, I had to think about this, which I thought was pretty awesome. So anyways, before I get into saying much more, and there's a ton to say. There's a whole theory. There's something called continued fractions, which is how you approximate. But this is actually really helpful if you're like working with a number that you would like to approximate. And I'll do this in my next video, but let's say you had some decimal or some batting average, 0.334, which is going to be part of my next video. 0.334 is right in between here. And so you could say, well, let's keep going until we get to it. And the problem is, for the batting averages, it takes a long time to get there. So it's hard to bat 334. You have to have a lot of at-bats before it's even possible. But that's my next video. Okay, let's say a few more things pulling from better visuals than mine. So here's from Wikipedia. I started to try to make this. Anyways, they show a few things. So they make it so you can highlight it. So there's those first two. And then what happens if I go a little further? So I'm going to show you down below. There's the next one. That's this. Those two. And then we'll keep going. Again, if you've never seen this, I wrote a little program to plop them out. Okay, there's the thirds. So there's actually spreading them out. Here it is with the thirds. You can already see they're not like evenly spread out. Fractions themselves are evenly spread out. Like if you were looking at all the tenths, it would be evenly spread out, 0.1, 0.2, 0.3, 0.4. But we're talking here about small denominators, and sometimes they repeat. So if you're only allowing 2s and 3s as denominators, that's not equally spread out. Okay, let's keep going. So now let's run it a little further. Boom. Boom. So that's that next one where we add in the 2s and the 5s. And now I'll just let it go, and I'll kind of highlight as we go over here. And we're throwing things in. So there's the 2s and 3s and 5s. Because they have a little thickness, they look like they overlap. And here's a whole bunch of them. So I haven't gotten to the point of all those fractions yet. I'm throwing them in. So anyways, that's the Farey sequence. And you can see, as if you want to know the next one in between any two neighbors, you add the numerators and you add the denominators. It's pretty amazing if you've never seen that. So incorrectly adding fractions actually has a meaning. Okay. We call it the mediant of those two numbers, but let's stop that. But you can see these gaps forming, and there's a big gap around 0.5. It's actually very big gaps around the first few fractions, and the gaps get smaller as you go, but because a third was one of the first fractions, it's our 0.33, there's going to be big gaps around 0.33 for a long time. And that's what I'll talk about in my video about batting averages. All right. So let's just say a few general things here. So again, if you want to keep going, you can say, well, I'm really interested in what's happening between a third and 2/5. So let's just build the tree from there. I'm approximating things that are between here and here. And incidentally, you can also, this explains where like approximations of pi come from with fractions. There's just too many things to be said. So let's say we're at that point and we want to keep going. We're going to add them. So again, we're defining this operation. And sometimes how it's defined is like this. We use a little like plus with like a circle around it or a box around it just so we don't get confused. And we say, okay, we want to add the numerators and add the denominators. That is not the sum of the fractions. It's a random fraction. It appears to be a random fraction between them. But we call this the mediant. And it's this number that's in between. So let's do it. 1 plus 2 is 3, and this is an 8. Notice it always gives you a reduced fraction. There's tons of questions to naturally ask. Why does this work? But that's it. So if your goal was to approximate something close to a third, you would then keep going and say, well, what's going to be in between these two? 4/11ths. It's just spectacular. What's going to be between these two? 5/14ths. And that's what I will do along with a few other things. And I'll look at some data from actual baseball. But if you start to see that this is what, if you're looking at possible fractions you can get with small denominators, the story becomes really interesting. Okay, I think I will stop there because I'm sure this video is already too long. But that's this idea of, if you want to learn more, look up Farey trees or Farey sequences. In the next video, I'll just talk about a couple other amazing visuals that go with this. But if you've never seen this before and you know you have two reduced fractions that are adjacent in the Farey tree, have come from this, basically two reduced fractions of small or close denominators, you can get the next closest by adding the numerators and denominators together. It's, like I said, it's really spectacular if you've never seen that before. Okay, I think I will stop there.